HYPRE is a package that differs from PETSI and Trilinos in that, whereas PETSI was just described to you as it does lots of different things from time integration all the way down to linear solves, et cetera. HYPRE is really focused on the linear solve itself. So parallel, large, sparse linear systems of equations. And one of the things we've done a lot of, and really a feature of this package, is multi-grid methods in particular. So let's see. There we go. OK, so here's the team right now and some former people. If you want more information, including papers and things like that that we've written, you can get them through this website here. Most of the talk today is focus on these interfaces for building a linear system, because this is one of the things that's a little bit different about HYPRE relative to other packages that are out there. OK, so let's start with the motivation now. Why multi-grid? We're interested in multi-grid methods because they're optimal as well, but in a slightly different way. In this sense, if you've got a linear system with n things to solve for, multi-grid methods will solve them with order n computations. So in that sense, they're optimal. And that also gives them good potential to scale. If you think of weak scaling, where you're growing the problem with the number of processors, you've got the potential to solve those larger problems in constant time. Whereas more classical methods, they might depend on the stiffness of the problem, so they might take more iterations for larger problems. And so even if you're adding additional resources, you still take longer to solve the linear system you're trying to solve. So that's why we care. So this is one view graph now to tell you what multigrid is. It's just a cartoon. Think a two-dimensional Laplacian. And since it's an iterative method, you take an initial guess. And suppose we were to plot the error, the difference between that and the exact solution. It might look something like this on this 2D grid. So there are two main components to a multigrid method. The first is called a smoother. It's just a relaxation method. It's something simple like Gauss-Seidel or weighted Jacobi, very local, simple process. And what happens when you apply this to the linear system, at least in this classical setting, is the underlying error becomes smooth. And so the second important part for a multigrid method is to realize that you can approximate that underlying error very accurately on a coarser mesh. So you can project the problem down here and solve a much smaller problem. And then if you were to interpolate this back up and correct your current iterate, you'd make very fast progress toward the solution. Now, in practice, this can still be a huge problem. So what we do is just reapply this concept, do additional relaxation here, go to coarser and coarser grids, all the way down to, in HYPRE, we'll go down to a single degree of freedom in some of the solvers. And then you interpolate all the way back up. This is called a V cycle in multigrid. There are lots of other cycles that you can use. This is the most common one used in parallel because it's the one that scales the best. Things like W cycles don't have good scaling properties in parallel, so we don't use them. So anyway, that's multigrid. And this is showing you the very classical setting. And it's on a regular grid, so I can draw nice, pretty pictures. But there are ways to do this on very complicated-looking grids, completely different problems besides the Laplacian. And there's this thing called algebraic multigrid, which has come up a few times, which is an attempt to apply this multigrid idea to just a system of equations. So you attempt to just take the fact that you have this a bunch of coefficients in a matrix, and then use that to build grids and do all these different things I just talked about. So you don't really have a grid, but you still try to apply these ideas to solve the problem. OK, so let me get into how to use the code and how to use these linear system building interfaces in particular. OK, so there's a couple of things before you use HYPRE that you need to do, and there's some decisions first. And so the first is you need to choose the linear system interface you want to use. I'll tell you what this means in a second. After that, you choose some solver or preconditioner, and then based on this, you have to choose some sort of underlying storage approach that is to be used with that solver. And then you can go and start writing your code. When you're building the system, it may require building some auxiliary structures like grids and stencils, and you'll see that in a minute as well. So you build your linear system, build your solver, solve the system, and get the information out. So just as a summary, this is how you use the package. And let me say more about this linear system interface stuff first. So we have a notion of a conceptual linear system interface, and I've got little icons up here to kind of demonstrate this idea. On the right, this looks like a regular matrix. You've got coefficients, row something, column something, that are non-zero. And normally when you're dealing with a linear solver package, this is how you describe your linear system to the package, as you say. This row something, column something is this coefficient, and you do that, and then you solve the system. However, one of the things HYPRE does is provide other interfaces. For example, something where you describe a grid and say a stencil on the grid and the coefficients on that stencil. And this provides some additional structure. And you can use that structure then to do methods like structured multigrid type methods, and also store things differently to get better efficiency. At the same time, you could use this interface for describing your linear system and still build a more general compressed sparse row type underlying storage, matrix storage scheme, and use something like algebraic multigrid, which is a more general method. So we provide different interfaces here, partly to give you access to solvers you may not have access to otherwise, as well as to make the coding easier. It might be more natural for your application to use some of these other interfaces. So this is sort of summarizing what I just said. And currently, we've got basically 4 of these interfaces in HYPRE. So they're called struct, struct, FEI, and IJ. This is for structured grids, or logically rectangular grids. This is semi-structured, I'll say, and I'll go through these 2 in examples in a minute. And then we support a finite element interface, which is actually designed at Sandia. And we also have our own flavor of the standard linear algebraic way of describing a linear system. Okay? So I'm going to now dive into these 2 with some example code. And I'll try to do it in a way that's kind of visual in form. Okay, so starting with struct, the structured one. So this is appropriate for structured grids with a fixed stencil pattern. I'll tell you what a stencil is in a little bit. It has a notion of, so we have to set up a grid in this interface. And so there's this underlying index space that's important. So these are just in 2D, if you think about what's drawn here, it's just tuples, so an I and a j. So I is sort of the x dimension, j is the y dimension, but they're all integral. And you describe this grid in terms of boxes, so you give it a lower and an upper corner, and that gives you a box of grid points. And you can use arbitrary unions of these things to describe your overall grid, and that provides some structure to HYPRE. Okay? And this interface is all for scalar problems. Okay, so here are the things you have to set up when you're setting up the linear system. There's a standard matrix and vector, but there are these other 2 objects, a grid and a stencil. And the grid and the stencil is what provides the structure in this setting. And I'm going to use a Laplacian as an example. This is a 2-dimensional one. And I'm going to do it on this funny 2-dimensional grid. Standard finite difference discretization for this, so this yields a 5-point stencil. I'll show you a stencil in a minute. And so the first thing for this problem that has to be done is you have to decide how to distribute it. And I'm going to distribute it this way. I'm going to choose this left half and put it on processor 0 and this on processor 1. This is a decision that the user makes. It's not a decision that HYPRE makes. So I'm going to do this for this example. And I'm going to I believe I'm going to describe processor 0's code. This is processor 0's point of view, the code. And all of the little movies I'll show you will have a little diagram here showing what we're trying to build. And then down at the bottom, we'll show you some code that has to be called. Okay? And I'll go through some of this quickly so you won't see all the details. That's not really that important. I want to give you an idea of how the interfaces work. So we're trying to build this piece of that grid I showed you before on processor 0. So the first step is to call the create function. You give it the number of dimensions in an MPI communicator, and it gives you back a grid object. And then we have to tell HYPRE what's in that grid object. And so we call this setExtents function, give it a lower and an upper corner, which gives it that little box of my grid. And then I call it again, and it gives me this box. And then I just call a symbol. And so now I've done processor 0's part of describing the grid. Processor 1 does something similar for its part. All right, so the grid's done. Now, the other part we need is a stencil. Just the 2's and the -1's are what is basically a stencil. So in 2D, the Laplacian would have 5 points. So you'd have a 4 here for the constant coefficient case, -1, -1, -1, -1. And this shows you the equation basically at this unknown value at this grid point. So it's a row of a matrix, okay? But it's described in a different way. You know, instead of me telling you it's row I, column J, -1 is the coefficient, I tell you grid point I, comma J, the west coefficient is -1. It's just a different way of describing a matrix, but it provides some structure, okay? So the way the stencil is set up is you call create, you give it the size of the stencil and the number of dimensions. It returns an empty stencil object here. And then you make a number of calls to the set element call. And you give it these offsets. And offsets are just an abstract offset from a cell center. So 0, 0 is the center. That's the center coefficient. And then I tell it what the west is. That's -1, 0. East is +1, 0. South, north. And I'm done. I have a stencil now. So I've got a grid and a stencil. This is the structure of my problem. And from there, I can go on and now actually fill in the non-zeros of the matrix. So the example 4 -1 I just mentioned is for a constant coefficient problem. But this HYPRE works for variable coefficient problems. So the stencil is just describing the structure. But at each grid point, I can put different coefficients there. They don't have to be constant. On the other hand, we have a way that you can actually tell us you have a constant coefficient problem, and then we won't store the whole matrix. We'll just store the stencil components themselves, the 5 numbers. OK, so for matrices, it's similar. I don't have a little movie to show you. You have a create, and you get a matrix object about. You call initialize, which just tells HYPRE I'm about to give you some coefficients. And then in this case, I'm setting values for. And I'm trying to show that you can do it for only a subset of the coefficients. So the center and the south coefficient, I'm passing in the 4, and 1. And I'm doing it in 2 calls, one to set those values over this box of grid points, and then another to set it over this box of grid points. Okay? So there's some flexibility on how you set the coefficients themselves. And then you do some special things to fix up boundaries. Again, it's the same, calling these same 2 routines, basically. And then call a symbol, and that's the matrix setup. This is showing you how you'd fix up the boundary. Again, you call a similar function here, and you might zero out that coefficient along the boundary, because it's a Dirichlet problem, and you don't want to have that be a non-zero number. Vectors are similar. Create, initialize, set box values again, but now you're just setting scalar quantities for the vector and a symbol. Okay? So that is how you would set up a linear system for a Laplacian on that grid on 2 processors. And of course, this extends to any number of processors. We also have the ability, if you just put between the create and the initialize call, this set symmetric line, it will store the matrix in a symmetric way if you have a symmetric problem. And that kind of gives you an overview of how you use the structured grid interface in HYPRE. The next thing is this semi-structured. So this is a generalization that allows you to describe much more complicated settings. I've drawn some semi-structured grids here. You might have block structure. You might have structured adaptive mesh refinement, or even overset grids. All of these things have a lot of structure in them, but they're not completely structured. And that's the idea behind this interface. And it generalizes a number of things. For one, it's not just scalar PDEs anymore. So I don't just have a value at cell centers. I can also have face-centered and node-centered values or edge-centered values in 3 dimensions, and any numbers and combinations of them that you want. And what else? OK, and because it's not fully structured, the way we do this is we introduce some new concepts. One of the main ones is a part. So a part is a structured component. And then you can have any number of these parts, and you can kind of glue them together in arbitrary ways. And then there's this extra object that we introduced called a graph, which wasn't in the structured interface. So, OK, so we build the parts in the same way I showed you before, basically from a grid and stencil approach. But we also have this a finite element stiffness matrix approach. And then between the parts, we can describe how they're related through this set neighbor part call, as well as this set shared part call. And I'll show you examples of that. I have 3 examples. I won't have time to go through all three. I'll try to go through the first two, and it'll probably be a little bit rapid, but you'll get a sense for how this works. Similar to the other case, we have these components that need to be built plus this extra graph component. Okay? So here's the first problem. It's a diffusion problem, and it's this block-structured grid. So each one of these 5 parts is structured, like the previous problem. I've also got more than one variable, not just cell center, but I've got x and y face variables. And so I've got 3 stencils that I have to describe in this problem as well. Okay? Now the way I'll do it for this example is I'll split the problem up into 5 parts, numbered in this way. And I'll also decide to distribute this so that each part is put on a single processor, so there'll be 5 processors. But again, this is completely decided by the user how to distribute the problem. I'm just doing that for today. And it looks like we're going to be looking at processor 3 of part 3's code. All right. So let's start with the grid. You say create, and this is what I'm basically trying to build in this example. I get a grid object back. I again call setExtents to give the lower and upper corner. Okay, and then the other thing is I have to make this setVariables call and tell it I've got cell-centered variables, x-face variables, and I have 3 different kinds of variables on this grid. Okay. Now at this point, every processor's got described a piece of the grid, but they're completely unrelated to each other. They're on completely different index spaces. So one way we can describe some relationship between them is through this setNeighborPart call. And in this example, I'll make this call here with all these arguments. And what it'll do is it'll describe this box of points in terms of part 3's index space and part 2's index space. And that provides a relationship between these points and all of the degrees of freedom or variables that are defined there in terms of 2 different parts. So it's a relationship now between the parts that we have. And I do the same thing between 3 and 4, and symbol, and I'm done. So a few words about this. There are issues with consistency. Well, okay, so one of the things that happens here is when you do this, this variable now becomes the same on 2 different parts. Okay, and HYPRE will deal with that internally. We'll actually deal with the fact that this is the same value, make sure we give you a consistent answer back when you ask for the answer back. Another thing to notice is that some of the variables might have different variable types on different parts. So in this case, for example, this variable right here is a y-face variable on part 3, and it's an x-face variable on part 2. This is another thing that HYPRE will take care of internally and deal with. Okay, we also have stencils here. I won't go through it. It's basically the same as the previous one. The only difference is that when we call this setEntry thing, we have to tell it the variable we're coupling to. And we have 3 stencils to do here, and otherwise it's exactly the same as before. The graph is the new thing. We call create, you get a graph object back. You give it a grid, you get a graph object back. You tell it what your 3 stencils are by saying setStencil. Okay, and then call a symbol. And now I actually know what the non-zero structure of my matrix is at this point. That's what the graph represents. Okay? And to set up the non-zero values, again, it's calls to these set values. We also have an add to values where you can not just set the values, but add to them. And same for vectors down here. And I won't show you how that works, but it's the same as before. Okay? Now, that was a grid stencil approach to doing a semi-structured grid problem. We also have a finite element approach to doing this. These routines are the new routines that are needed to do the finite element style approach to doing semi-structured grids here. And let me show an example. So it's this star example. Again, it's a Laplacian. So instead of having a stencil, I'm going to actually pass in lots of finite element stiffness matrices. And an element in HYPRE is basically a cell in 2D, okay? So if you had triangles, you'd actually take the combination, the sum of the 2 triangles, and that would be your element when you're interfacing with HYPRE. Okay, so I'm going to be passing in these 4x4 stiffness matrices that get summed up, and that's how you generate the discretization for this problem. Again, yeah, sorry.
Just curious, how do you deal with the singularity in the middle?
Oh, I'll show you. Okay, so again, I'll split this up into 6 parts, numbered in this way, and I'll put 1 part on a processor, just for simplicity. Again, users decide this. So we'll do 6 processors, no stencils, right? And we'll look at part 0, this one right here, okay? So setting up the grids, a lot like before, you call create, get the grid object back. You call set extents to set the extents for the grid. And then you set variables. So you tell it I've got nodal variables, okay? And so now here's one of the new routines. I have to, I can specify what the ordering is of the variables on a cell here, on an element. So 0, 1, 2, 3 is what I'm choosing, and I do that through this call here. And then now, as in the set neighbor part, I've got a new routine, which is almost the same. It's called set shared part. And instead, what I'm doing is I can say all the variables along this face are the same on part 0 and part 1. So this provides some relationship now between the parts, just as before, but not over a whole cell of quantities, but over just a face quantities. Same for part 0 and 5. And then here's the singularity point you were asking about. 0 and 2, 0 and 3, 0 and 4 all share that degree of freedom there. HYPRE deals with the fact that this is all shared and sets up the matrices and makes sure the solution comes back right and all that stuff. And then assemble. OK. So that's the grid. The graph object is like before. And the only extra thing you need to do is call this set FEM call, and that just tells HYPRE I'm not going to be passing in stencil quantities. I'll be passing in stiffness matrices. And you assemble, and you've got the graph. OK. And then to set up the values now, instead of set values, we have the new routines add FEM values, finite element values. And here you give it an index, for example, and you give it the values in your stiffness matrix. So you're basically just passing in stiffness matrices, and HYPRE assembles these things. So it's very similar to the other example, but it's a finite element style for setting up the coefficients. Okay? AMR I won't talk about here. Currently in the code, you have to use this graph add entries call to sew together the coarse fine, the way the coarse and fine interfaces couple to each other. And this is sort of the catch-all routine that allows you to couple things in any way you like in the semi-structured setting. OK, I mentioned you can call AMG even though you're calling this semi-structured interface. And you do this by, between the create and initialize call, you set object type and tell it to set up a compress parse row object or some other thing that some other solver might need. So we can build different kind of underlying matrix structures with this. OK, so that's 2 of the interfaces that are a little different in HYPRE. Solver-wise, this is kind of a list of what we have. I'm not sure if it's completely current, frankly. Here are the interfaces, and the check marks tell you which solvers you have access to if you use through these interfaces. So semi-struct, for example, gives you access to any of these solvers. The first ones here are for multi-grid methods. SMG and PFMG are on structured grids. This is for semi-structured grid problems. This is for general matrix problems, and down here, sort of the matrix-free Krylov solvers. These are all in HYPRE. The way you create and use a solver is pretty much the same as what I showed you in the interface. You have a create call, gives you a solver back. You set certain parameters that are specific to the solver, like the convergence tolerance, maybe a lot of some other things. Call setup, solve. You get the values out, and the way you get the values out is again through this conceptual interface I just showed, and then you destroy it when you're all done. So those are the main calls. This is an example where I'm using SMG, which is a structured multigrid solver, as a preconditioner for CG. So you basically make those calls I just showed you to kind of set up the SMG solver. Do the same thing for PCG, and then you pass the SMG solver into the PCG solver through this set precon call. That's how you build a preconditioned conjugate gradient method in HYPRE. Just a little bit about a few of the solvers. I mentioned SMG just now. These are for structured grid problems. PFMG is another solver that's available. They take advantage of the fact that this is structured and has stencils, and so they're cheap and fast. This is a very old plot. We've scaled this. We've shown weak scaling up to 1 million cores of our current machine at Livermore, and it scales pretty nicely. So, and that took a lot of research to achieve, which I won't talk about today. And then we have this AMS as solver is for solving Maxwell's equations of this form. This is the definite Maxwell equation. It's a very nice solver. It deals with lots of different issues with jumps and coefficients, strange cell aspect ratios, all these things. And it uses the Boomer AMG solver underneath it to do that. We also have some non-multigrid solvers like sparse approximate inverse and IOU. And I mentioned the website before. You can get the code as well as papers, all these kinds of things there. Building the library is pretty straightforward. You basically type configure and make. You might have to configure some specific things, so you configure -- help will give you a list of options. Everything's written in C, so it's pretty portable. It's not too difficult to build this. And it builds pretty quickly, too. Actually, on my Tux box at work, I can build it in like 10 seconds, which is nice. We have a Fortran interface. The Fortran interface pretty much mirrors the C interface. And that's really the only way we document it, too. You have to look at the documentation for the C interface and understand how to do the translation to Fortran. OK, and then we also have this HYPRE support. If you've got questions or comments or whatever, this is the place to go. And it'll automatically assign a number to it. We'll track it and try to answer your questions as best we can.
The multigrid is very successful on the elliptic. How good is it for other types of problems? I just noticed you Maxwell equation there.
Yeah, it's best for elliptic problems. It's not a solver that works for any linear system that you give it, even though that's what we attempt to do with AMG, with algebraic multigrid. In reality, there are lots of knobs to turn, and the algorithm can vary if you're solving elasticity versus diffusion versus the Maxwell equations. So it doesn't work for all problems, but it's pretty successful over a wide class of them, I'd say.
Just for clarification, do you also allow for mismatch at the interface between the nodes, or at least the nodes must match?
In the examples I showed you, they have to match. If you use that catch-all routine I mentioned, where you just add arbitrary graph entries, then they can be mismatched. But you have to do more work to use that call. It's more like calling an IJ interface, where you specify things in much more detail and you get away from the structure a little more.